All right, good morning. I see that a lot of people are here. That's good. We have forgot to announce that it starts half an hour earlier. I'm wondering whether there is a group half an hour later rolling in with somewhat tired eyes and there's no coffee left. Well, the first talk this morning is given by Bren on the NMR spectroscopy of paramagnetic molecules. This is for the first time that we have this topic at all at our workshop, and we are very happy to expand our range of topics and techniques here. Kara and Jesse are offering practicals that, from what I hear, are extremely well received, and we look forward to the talk telling us about the details of this technique. Thanks, Kara.
Okay. Thank you very much, Karsten. So I'm very glad to be here and have a chance to hopefully convert all of you into believers in NMR of paramagnetic molecules. So this is a technique that is really underused in inorganic and bioinorganic chemistry, especially considering that we all have access to NMR spectrometers. And you don't really need special equipment to do this. You just need to be willing to take an NMR spectrum of your paramagnetic molecule and give it some thought. So despite that, I still often hear, I'll go to seminars and I'll hear people say things like, we got to product 3 and it was paramagnetic, and so we couldn't take an NMR spectrum, and so we went on to such and such, and I just go, ah. But usually, though, it's organometallic chemists who offend in that way, not so much bioinorganic chemists. But it is true that it can be challenging sometimes to get high-quality, high-resolution NMR spectra when your sample's paramagnetic. But even in that case, there is a lot of information in the spectra, even when you have sort of difficult conditions and broad lines like you can get. So I'm going to show you a number of examples of how you can get information on electronic structure of your compound by analyzing some of these properties of your spectrum. Okay, so this is just a summary of what I'll be going over today. So I'm going to just start out with some introductory material. I will go over what will be a review for you of NMR fundamentals, just to make sure we're all on the same page. And then I will spend some time talking about nuclear relaxation in NMR, because that becomes very important to understand some of the fundamentals of that when you consider NMR of paramagnetic systems. And then I will talk about mechanisms and examples of effects of unpaired electrons on relaxation and on chemical shifts in NMR spectra. So I have a number of resources to recommend. Oh, and one other comment I want to make is that I uploaded a set of slides about 24 hours ago, and then I uploaded another set of slides about 12 hours ago, and the more recent version has _update on it. So the first version is fine, but I can't stop myself from tweaking things. So if you want the most updated one, make sure your file says update. All right. So I want to introduce to you some of my favorite resources in this area. So this is an oldie but a goodie, a book by Bertini and Lukinat. This is a really nice introduction to the subject. It has a lot of examples in it. And I also like this Coordination Chemistry Review article. This is probably the one that I use as a reference myself the most. And then these are a little more specialized. So this is a monograph by Lucia Banchi specifically on nuclear and electron relaxation. And those of you who are interested in EPR spectroscopy might also find this to be a really useful resource. And then recently we published a chapter on analysis of spin densities, in particular using NMR. So that's, again, a little bit more specialized and in-depth if you're interested in that. Okay, so I'm going to start out just by showing you a few different representative spectra of paramagnetic metalloproteins. So I will be focusing on metalloproteins in this talk. All of what I talk about will be applicable to small molecules as well. In some cases, some of the considerations are a little different, and I will be pointing that out when we get to that point, but I will be focusing on proteins since that's my area. All right, so first example I'll be showing you is horse fairy cytochrome C. So this is low spin iron 3 protein with a heme. The heme is axially coordinated by a histidine and a methionine, so it's a low spin, spin 1/2 system. And so this is the system those of you taking the practical have examined or will be examining. So some of our favorite protons to look at in this spectrum are the 4 methyl groups that are alpha to the heme macrocycle. And so here are, these are actually mutants of cytochrome C. And this is a mutant where we mutated the axial methionine to alanine, and this is actually just the wild type. But in both cases, we ligated a cyanide trans to the histidine. Right? So as you see, these spectra, we have a big crowded region here in the middle between 0 and 10 parts per million. So that's sort of our normal proton NMR range. And so as this is a 12 kilodalton protein, not a huge protein, but it has a lot of protons, so there's a lot of peaks here. But then outside of that range, in the low and high frequency regions here, we have a number of other peaks, and I've starred the 4 heme methyls, and you see those really pop out of the spectrum and are really easy to identify. So this low spin iron 3 case is really sort of the best case for getting high resolution spectra of a paramagnetic compound. Because we have really pretty minimal line broadening. So your peaks, even though they're quite shifted, are really very narrow. And so you don't really have to use special techniques in order to detect these. Okay, so now this is another cytochrome C. In this case, we had mutated the axial methionine that's present to alanine, but now we have water bound in that position. And it turns out in this particular protein, we have a high spin, low spin mixture. And now you see that our 4 heme methyls that I've labeled here are between 40 and 55 parts per million. So we have significantly higher chemical shifts. And we also have more line broadening. But the lines still are not terribly broad. So now we're moving on to copper. And so this is where things get a little bit more scary. So copper 2 azurine, also spin 1/2. All right, but now you see we have really broad lines. And if you didn't know there were peaks here, you might just think that your baseline was terrible. All right, but these are peaks belonging to the histidines here in azurine. And the cysteines we can't even see in the spectrum. And I'll show you later some tricks we can do in order to find those cysteine beta protons here. All right, so quite large shifts, but really quite extreme line broadening. So if you don't like the way that looks, one thing you can do is substitute the copper with nickel. And now that gives you much more narrow lines. So this is a spin 1 system, so higher spin, but not as broad lines. But now we have really high chemical shifts, so now we can see those cysteine beta protons. And they have chemical shifts out to 250 parts per million. And then finally, another copper protein. So this is also copper 2, spin 1/2, but it's this copper 2, copper 1 mixed valence site in the thermus thermophilus copper A domain. And so this has this really cool active site structure with this dinuclear copper site bridged by the 2 cysteines. And now this is really quite different from the copper 2 system in azurine. All right, so in azurine you had those really broad lines. And here the lines are much more narrow, so we're going out to about 35 parts per million. And these are definitely broad peaks, but they're not so extreme as azurine. And then there's also some peaks going out to 300 parts per million that are obviously quite a bit broader. It turns out these are the cysteine betas here. Okay. So I will be referring back to these spectra as I go on. And by the end of this talk, you will all understand everything about all of those spectra, I hope. All right, so I just want to make a few comments about some of the things that we can learn from analyzing these kind of data. So Dean mentioned yesterday in his talk about ITC that you can analyze those data on a lot of different levels. And the same thing is definitely true for paramagnetic NMR, in that you can just take a quick spectrum of your sample, and from that, by comparing to other compounds, you can determine your metal oxidation state and your spin state. And you can just stop with that and move on. So you don't have to get into it into more detail. But you can also then get into a very high level of detail. So from these spectra, you can do things like estimate your electron spin relaxation time. And that then is related to features, electronic structure features of your compound. In particular, the presence of low-line excited states is a major factor that influences that electron spin relaxation. You can also assess the extent, and then if you get assignments, the pattern of unpaired electron spin delocalization onto cofactors and ligands. And you can also, if you do some analysis, extract hyperfine coupling constants. So this is the same hyperfine, these would be super hyperfine coupling constants in EPR, but we'll just call them hyperfine coupling constants. So we're looking at coupling constants between a ligand proton and the metal. Okay. You can do things like assess the presence of hydrogen bonds. So if you have a second sphere interaction, you can verify that that's in place by analyzing these spectra. You can determine the magnetic anisotropy and the magnetic axes of your system. And so this is something that we're doing in the lab practical, so some of you have already done this, and some of you will do it later. You can refine a structure, so you can take a structure that's known, determined using some method. Maybe it's a computational structure, maybe it's a NMR structure, and you can use the parameters that you extract from paramagnetic NMR in order to significantly refine the structure. And this works so well that now people who aren't even inorganic chemists routinely introduce paramagnetic metals into their proteins or paramagnetic probes on their proteins in order to make in order to improve their structure. And then in addition to that, you can do all of the things that you do with NMR anyway, which is already a powerful technique, determining structure, looking at exchange phenomena, looking at dynamics, etc. Although sometimes your ability to do some of these things is hampered by the effects of the unpaired electrons. So now in cases where you have narrow lines, like the cytochrome, that's the low spin iron 3, you can do all of this. In things like the azure and the copper 2 with the really broad lines, you start to lose your ability to do a lot of these things. Okay, so now I will review NMR fundamentals, and I'll go through this pretty quickly because I think you all already know this, but I just want to make sure that we're all on the same page, especially when we get to talking about relaxation. It's important that we all are talking about the same thing. Okay, so we can detect NMR spectra for nuclei that have non-zero nuclear spin. So again, you'll see a lot of parallels to Art's talk about EPR. All right, so we have, think of it as a spinning charged particle, and then we have with that associated a magnetic moment that's described here. And so there's a lot of analogy here, again, to EPR. And I'm kind of starting with equations that are similar to the EPR equations so that you can see those parallels, and then I'll switch to the NMR. We just sort of use different language, but it's really a lot of the same sort of phenomena and ideas. All right, so there's a nuclear G value here instead of the electron G value. For the proton, it happens to be this. All right, so as long as you have non-zero spin, you can, in theory, detect an NMR spectrum. The nuclei that we most commonly use in NMR are spin 1/2 nuclei. But there are nuclei with higher spin values that also you can detect NMR. And N14 and deuterium are commonly used. I'm going to focus entirely on spin 1/2 systems. So these nuclei that have spins greater than 1/2, these are quadrupolar, and so these have additional relaxation mechanisms themselves, so they're broader even in the absence of an unpaired electron. And then when you have them interact with unpaired electrons, you have yet additional broadening that can make things quite difficult. But these are the most common nuclei anyway, especially protons. And protons are our favorite because they're on most of our molecules, and we're just very lucky that protons happen to have the highest magnetic moment of all nuclei. Well, actually, tritium has a higher magnetic moment than protons, but we don't do tritium NMR very much. So protons are high magnetic moment, and it turns out to give us high sensitivity. Okay, so if you have a spin 1/2 nucleus, then you have associated with that I of 1/2 MI values of plus or minus 1/2. But those states with those different MI values are degenerate in the absence of a magnetic field. And another way to think about that is that they orient randomly. But then when you apply a magnetic field, these magnetic moments align with or against the field. And they will either align with if their MI value is plus 1/2 and against if it's minus 1/2. And these then correspond to a lower energy state and higher energy state. So then when we put energy in the system in order to see an energy transition, you can think of it as flipping a spin between up and down. Okay, so another way to think about this, so the energies of those two different states we can express here with this equation. So we have the two different MI states and we have two different energies. And so the energy depends upon the magnetic moment of our nucleus and also the strength of our magnetic field. And so as you increase your magnetic field strength, you split these two MI states, and your energy, your transition is expressed here. And so the greater this energy change, the more sensitive your experiment is going to be, because you have a greater Boltzmann population difference between your lower and higher energy states. So this is why we like to have nuclei with a relatively high magnetic moment, like protons, and why we like to use stronger and stronger magnetic fields. So that increases sensitivity by increasing this delta E. Okay, so switching over to the constants that we use more commonly in NMR. So traditionally, the magneto-gyric ratio, and also called the gyromagnetic ratio, I might end up using both. They're the same thing as each other. So that is this equation here. So it's just the ratio of the magnetic moment to the angular momentum. So it's just proportional to the magnetic moment. So you can just kind of think of it as a substitute for that. So using the magnetic gyric ratio instead, then our resonance condition is written here. Delta E equals gamma B naught over 2 pi, which is h nu. Okay. All right. So as I mentioned, we have this small energy difference between these two states, and that gives us a Boltzmann population, slight excess of the lower energy state, which is spin aligned with the field. And so instead of thinking of individual spins, we can think of a net sample magnetization aligned with a z-axis that we call mz. And so it's often easier to think about that as a single net vector like this, right? So when we do NMR spectroscopy, we are taking that net magnetization vector and perturbing it. And we perturb that with a pulse that's oriented 90 degrees to that vector. And by the right-hand rule, then, that tips that sample magnetization down into the xy plane. And then when you turn off that pulse, that relaxes back to our equilibrium position. And then after that relaxes back, you can apply your next pulse and do your signal averaging. Okay. So the time of the pulse determines how the time of the pulse can be adjusted to determine how far down you flip the signal. And you get the highest sensitivity if you flip your magnetization down by 90 degrees into the xy plane, because we measure our signal here in the xy plane. Okay. So instead of thinking of a single vector, you can also think of this sort of as a cone of precession. So if you are not, so in the laboratory frame, so before we were sort of in the rotating frame, but in the laboratory frame, your sample magnetization is precessing with a frequency that is equal to our Larmor frequency here, so in radians or in hertz, according to our resonance condition here. So that precession is then our characteristic frequency that we're going to measure in our NMR spectrum, and then we will convert it to ppm. Okay? And so now when we do our pulse, we're actually tipping this whole cone down, which is precessing into the xy plane, and then we will be able to see that frequency of precession and measure that, and that then is going to be reported as our frequency in our spectrum. Okay. So when that signal is measured is when the signal is relaxing. Okay, so you apply your pulse, you're tipping this down, and then when you turn off the pulse, that's when you turn on the receiver. And then in the receiver, you're measuring this amount of magnetization along one axis here. And so you see an intensity that is wiggling at this frequency, the nu naught frequency here. And the intensity of it is decreasing with the characteristic time constant. So that you can fit this then here to get your relaxation time, T1 and T2. Okay. So actually you would get T2 from fitting this. So T1 and T2 are two different characteristic relaxation times. So the T1 refers specifically to the relaxation along the z-axis. And that's also called longitudinal relaxation time or spin lattice. And so that occurs by exchange of energy between the surroundings and the spin. There's also relaxation that occurs as this comes back. You have relaxation in the XY plane, and that's the T2 value. And that occurs by exchange of energy between spins in the sample. So I'm going to be assuming in this talk that T1 and T2 are equal to each other. And that is the case in what's called the fast motion regime when you have a small molecule. So it doesn't strictly actually apply to proteins, and a lot of the samples I'll be talking about. However, that's okay, because we can ignore that complication and still cover all of the fundamentals that I'm going to talk about today. But it does turn out that there are a lot of things that will contribute to T2 and not T1, so those will diverge once you get to larger molecules. And so that's something that is kind of would be a next lecture, I guess, beyond this first one. All right, so then you get your FID. I think you've all probably seen these, right? And so this is our signal in the time domain, and then you do a Fourier transform to change this to the frequency domain. So then you get, here's our frequency right here, and then you get a characteristic line width, and that line width is just 1 over pi T2, where T2 is this relaxation time that we see here. Okay? So the faster this is relaxing, the broader our line is going to be, and that's just an expression of the uncertainty principle. All right, so you've probably seen frequencies in your NMR spectrum, but we usually convert them right away to chemical shifts, right? So a chemical shift is a relative value to the frequency of a reference, and we report it in parts per million. So that's just a more convenient measure to use rather than reporting parts per million of many hundreds of megahertz, right? So now you all learned in organic chemistry and have used in your own work, I'm sure, thinking about chemical shifts, using that to assign ligands and other compounds. And so you're all familiar with the concepts of shielding and deshielding and what kind of chemical shifts you normally get in your molecules. So I want you to erase your brain of all of those ideas, because we are not going to be talking about shielding and deshielding and electron density at all. So the factors that determine chemical shifts in paramagnetic molecules are completely different. All right, so don't even think about that. All right, so now when we go into a sample that has unpaired electrons, we now need to start thinking about this interaction between our nuclear spins and the electron spin. And again, Art made some of the same sort of analogies that I did, so you saw some of these ideas already. So electrons and nuclei have a number of different of similar characteristics that we can use to describe them, especially when we're focusing on spin 1/2 nuclei. So they have a magnetic moment. There's a gyromagnetic ratio. So there is a gyromagnetic ratio for the electron. It's not usually used. But you tend to use magnetic moment of the electron and gyromagnetic ratio of the nucleus. We describe the transition frequency in a field of strength B naught. So now I'm using the typical EPR equation and the typical NMR equation here. But these are the same idea. And these are our quantum numbers that characterize our two states that we're visiting. Okay, so they're very similar to each other in a lot of ways, that we can think of them as spinning particles with magnetic moments. But there are two really important differences between electrons and nuclei. So the first is that the magnetic moment of electrons is much larger, 658 times greater in magnitude. And so that's going to mean that we have a larger resonance frequency. So this accounts for the fact that we're in the microwave range for EPR and the radio frequency range for NMR. But also that larger resonance frequency, along with many other factors, including the second one here, leads to much more efficient relaxation for electron spins. So I talk about the relaxation of a nuclear spin between the upper energy level and the lower energy level by T1 and T2. And you can characterize this also for that electron spin going between its two ms values. So for nuclei, those relaxation times are often very slow. So even for protons, which relax fast compared to a lot of nuclei, a normal relaxation time would be something like a second for a proton in a small molecule. For unpaired electron spin, relaxation times for transition metals will range from 10 to the minus 13th to 10 to the minus 8th seconds. So we're in a completely different time regime. And that's going to have some important implications for looking at NMR of these systems. A second factor that's important is that electrons are in orbitals. So you get delocalization of the spin and spin-orbit coupling, right, which have a number of different implications, and I'll especially be talking about delocalization. All right, so next step, going to look a little bit at relaxation mechanisms in NMR before we get to paramagnetic samples so that we can understand the fundamentals of that. All right, so I already showed you how when we're collecting our signal while our sample magnetization is relaxing back to equilibrium after being tilted down into the XY plane. So that's our observation time when that's relaxing. And so as that relaxation time changes, our line width changes. Again, I mentioned that we're assuming T1 equals T2, so I'm just going to say T1 or relaxation time. So now a relaxation in NMR has to occur again by exchange of energy. It has to be induced, right? So we need some sort of frequency of electromagnetic radiation that matches our resonance frequency of our nucleus in order to have this exchange of energy and induce the relaxation of the nucleus. And so we will be considering unpaired electrons as a source to induce relaxation. But without unpaired electrons, there are other mechanisms that are in place. So these are some of the key mechanisms, and these I'm not really going to mention. This is just to show that there are others. But I'm going to focus on dipole-dipole relaxation, which is the dominant relaxation mechanism in cases where you don't have quadrupolar nuclei and some other considerations. So in dipole relaxation is a through-space interaction modulated by molecular tumbling, causing a fluctuating magnetic field. Okay, so in dipole-dipole relaxation, we consider, so here's our spherical protein, and we're going to pretend we have just two spins here. All right, and so what's happening is our protein we're in solution, and I'm going to be assuming we're in solution for everything here. And so this is undergoing rotational diffusion with a characteristic correlation time that you can estimate, assuming it's a sphere, using this equation here. And so as this rotates, these magnetic moments dipoles are rotating. And you actually have a whole range of rotation frequencies that are associated with this particular correlation time, and this is known as a spectral density. And within that range of frequencies, there's going to be somewhere a frequency that matches the resonance frequency of your nucleus, right? So this rotation of this molecule with two, or actually with many dipoles in it, or magnetic moments in it, will set up this relaxation field to induce relaxation. So the characteristic time, this correlation time for tumbling, then becomes very important for determining the relaxation properties of your nucleus. So the relaxation rate depends upon that correlation time. It also depends upon 1 over r to the 6th. So if we're assuming that we only have two magnetic moments that we're dealing with, 1 over r to the 6th distance dependence of this phenomenon. And it also depends upon the squares of the magnetic moments. All right, so this is where protons will relax much more effectively than all other nuclei that have lower magnetic moments like C13 and N15. So if you've taken a C13 spectrum, you notice that your lines are super, super narrow, and that's because the smaller magnetic moment decreases the effectiveness of this dipolar relaxation mechanism. Okay, so that was a very short section on relaxation mechanisms. So especially dipole relaxation is important, and we'll see how it's important in paramagnetic systems. So now we're considering a system where we have one or more nuclei we're looking at, and now we have one or more unpaired electrons. And so I mentioned that the magnetic moment of an unpaired electron is 658 times greater than that of a proton. And so I mentioned that the enhancement of relaxation through this dipole-dipole through space mechanism modulated by molecular tumbling depends upon the square of the magnetic moment. So now that we have a magnetic moment of our electron that's 658 times greater, we have a really effective means of enhancing relaxation of the proton through this dipole-dipole interaction. And so this is the equation that we use to describe the enhancement of the relaxation of a nucleus, where that nucleus has magnetogyric ratio gamma I, by an unpaired electron. Okay, and I'm using the Bohr magneton and G value here. And so these values are squared. And then this also depends upon the spin of the system. 1 over r to the 6th between the electron and the nucleus in question, and is proportional to this correlation time. Okay. So this is one reason that you have broad lines in NMR spectra, because this unpaired electron with this very large magnetic moment is really effective at enhancing the relaxation through the dipole-dipole mechanism. That gives you a large relaxation time. So the relaxation rate. So the relaxation rate is just the inverse of the relaxation time. So a fast relaxation rate gives you a short relaxation time, and that gives you then a broad line by that uncertainty principle. Okay, so now one complication here is that there is a little bit more to this correlation time. So I'm just going to pause for a second. I haven't seen any hands or anything, but I encourage you to ask questions, and maybe I'll stop for a second to see if there's any requests for clarification at this point. So, nope, you're all still sleepy. All right, so, I will move on then to talk about the correlation time. All right, so this correlation time is the molecular tumbling time in a diamagnetic molecule with no chemical exchange. All right. But there are other things that can give you these fluctuating magnetic fields. So the correlation time is important because you have this fluctuating electromagnetic field set up by the rotation of the molecule with the magnetic moments within it. But other things can do that. So one is chemical exchange. All right. I'm going to assume no chemical exchange, though, so we're going to take out that complication. The other thing is the electron spin relaxation time itself. All right. So our electron is going between spin plus or minus 1/2 states, ms plus and minus 1/2, all right? And when the electron relaxes, that also induces a fluctuating magnetic field that can induce relaxation of the proton. So it's not only its magnetic moment rotating as a molecule is rotating, but also the relaxation of the spin itself can have that effect, okay? So that means that not only the tumbling time of the molecule, but also the time that it takes for that electron to relax becomes important for defining the correlation time, where the correlation time is really just this, you can think of it as sort of an effective interaction time for the electron and the nucleus. That's not really quite physically right, but I find that a useful sort of concept of how to think about it. All right, so to determine your overall correlation time, then that's going to go into this equation. Again, it's important because it's proportional to your relaxation enhancement. You could just add the inverse of the rotational correlation time, the electron spin relaxation time, and time constant for any chemical exchange. Okay. So we'll assume no chemical exchange, so then we just have a rotational correlation time and electron spin relaxation time. So in a diamagnetic system, then, of course, this drops out, and our correlation time is just defined by molecular tumbling. Okay. But we're going to have to consider this case, where we have not only molecular tumbling, but also this electron spin relaxation time. All right, so this is where it gets very interesting when you are looking at different molecules with different transition metals in them with unpaired electrons, because electron spin relaxation times are really variable. All right, so this rotational correlation time can change over a few orders of magnitude as you go from small molecules to large molecules, but electron spin relaxation times vary over a much greater range. So 10 to the minus 8th to 10 to the minus 13th. All right, so that variation then is going to have a really big impact on your line broadening in your spectrum. So I'm doing this, making a simplification here where I'm saying, so our rotational correlation time ranges from about nanosecond to 100 nanoseconds, say. This is getting to be a large, kind of a large system for NMR. This would be a small protein, so cytochrome C would have a rotational correlation time in this range. Small molecules, though, would be down in more like 10 picoseconds or something. So that's a different situation, but I'm going to assume proteins here. And the electron spin relaxation time falls in this range, but once you get to really long electron spin relaxation times, you get the extreme line broadening, and that becomes more difficult to work with. So the systems we do the most NMR on have electron spin relaxation times in this range. Okay? So we'll assume this range of rotational correlation times and this range of electron spin relaxation times. And comparing those two, in most cases, our rotational correlation time is going to be much smaller than our electron spin relaxation time. So our spin relaxation time dominates our situation here. So we have, for example, iron 3 cytochrome C, our rotational correlation time 10 to the minus 9th, our electron spin relaxation time 10 to the minus 13th. So when you add the inverse of those two, our correlation time is the spin relaxation time. So whichever one is fastest is going to dominate our correlation time. So that means now in cytochrome C, the tumbling time is not so important. All right? So the tumbling time doesn't determine our correlation time anymore. Instead, it's this relaxation of the spin, and that characteristic time will then be proportional to our enhancement of our relaxation. Okay, now a few caveats. So that was a simplification saying now we're going to only care about electron spin relaxation time, and that's for the most part, that's true. Okay, but if you have a small molecule and a relatively long electron relaxation time, then instead your correlation time can still be your rotational correlation time. Okay. So for example, if you have a copper 2 complex that's relatively small, your tau s is 10 to the minus 8th, and your tau r is 10 to the minus 12th, so now your correlation time is your rotational correlation time. All right. But in proteins that give you pretty spectra that you can analyze easily, it'll be tau s. So I'll mostly use that as a simplification. And so when we have correlation time here, think of that as the electron spin relaxation time, the T1 of the electron. Okay. So that means then that variations in that electron spin relaxation time are really critical in determining your properties of your spectrum, and in particular the relaxation enhancement and the line broadening. Okay. So it's helpful then to look at some examples of a few different common systems, and there's a more comprehensive table in this reference here. But here's just a few different biologically relevant samples, examples of metals, the oxidation state, spin state, coordination number, and then the corresponding electron spin relaxation times. Okay, so you'll see that, for example, iron 3, low spin iron 3, we have quite fast electron relaxation time, as I've mentioned. And then because that number is small, we have really quite small line broadening because we have minimal enhancement of nuclear relaxation. Okay? And that's why the cytochrome C spectrum I showed you had really very narrow lines in it. Okay? Now, in comparison, the spectrum I showed you of azurine, this copper 2, spin 1/2, that has quite long electron spin relaxation time. And so that's why we saw this significant line broadening. All right, so these line broadening values here are calculated for a proton 5 angstrom from the metal. Okay. All right, so what's interesting here is how variable this is, all right, and how sensitive it is to changes in not just oxidation state, but things like coordination number. Okay, so for example, iron 2, spin 2, if it's a coordination number of 4, you have 10 to the minus 11th electron spin relaxation time, and not horrible, but quite a bit of line broadening. But if you increase the coordination number, then you have really quite minimal line broadening. And again, this is all just related to the mechanisms that are available to electron spin relaxation. And the most effective way to enhance the relaxation of your electron spin is to have low-line excited states that are able to interact with that ground state, and that interaction helps enhance that electron spin relaxation. Okay? So systems like copper 2, manganese 2 especially, do not have low-line excited states, and so you have really inefficient electron relaxation and extreme line broadening. So manganese 2 here, so this is really ugly, 100,000 hertz line broadening. Okay? So that's over many spectra that you would normally collect. That is your line. All right. But this is the reason why, a couple of things. So this is the reason why manganese 2 compounds are effective MRI contrast enhancement agents. So in order to work as an MRI contrast enhancement agent, a compound needs to enhance the relaxation of water nuclei. And so those compounds that have really long electron spin relaxation times and then in our NMR spectrum gives us a lot of line broadening, also is really doing a great job at relaxing all of the water and giving you enhancement of your MRI signal. So that's why manganese-2 agents are used for MRI contrast. Gadolinium-3 is the same situation as manganese-2. But here, go to manganese-3, different situation. You have low line excited states, and now you have not nearly as severe line broadening. Okay. So the fact that you get this enhancement of of nuclear relaxation, I've mostly been presenting as a problem because it gives you broader lines. But it doesn't have to be a problem, okay? So in fact, people have really caught on to the ability to use this enhancement of relaxation in order to get structural information, because our enhancement of relaxation is inversely proportional to 1 over r to the 6th, and that's the distance between your unpaired electron, where it's mostly delocalized, and the nucleus that you're looking at. So if you know all of these parameters and you measure your relaxation enhancement, you can estimate a value for 1 over r to the 6th. And so this approach is often called paramagnetic relaxation enhancement. And so the idea is that you would attach a paramagnetic molecule to your protein and find which of your peaks in your spectrum are line broadened. And this would usually be, of course, done on a 2D spectrum, right? And then the amount of line broadening then can be related to the distance from the probe. And then as you move the probe around, you can start to extract distance information. And so this is now routinely used, again, even by people who are not inorganic or bioinorganic chemists, but people who do biomolecular NMR will take advantage of this technique. All right, but there are some dangers here, because using this equation assumes that you have dipolar relaxation completely dominating your relaxation. And often that's the case, but not always. There are other relaxation mechanisms. And I will talk briefly about just one other. But in addition to that, there are a number of other ones that can come into play. So there are some dangers with that. You do also have to think about T1 versus T2 or R1 versus R2. So if you're measuring line broadening, you're actually looking at T2, which may deviate from T1 for larger molecules. All right. So in order to use this effectively, you have to have a little bit more awareness of some of these subtleties. All right. But even missing those points, you can still get some pretty decent estimates of distances, and especially relative distances, using this kind of approach. All right. Oh, and here are some of the other effects on relaxation. I'm going to talk about contact. Okay. All right, so contact relaxation occurs as a through bond interaction between your unpaired electron and your nucleus, or more specifically, you have to have unpaired electron spin density at the nucleus that you are examining. Okay. So the enhancement of relaxation by the contact mechanism depends on this quite simple equation. So again, we have tau s popping up. So now tau r is never a factor. And that's because this is a through bond phenomenon, so it doesn't care about rotation. It's just going right through the bond. It depends on the square of the hyperfine coupling constant, and then also spin. All right. So usually, though, especially in macromolecules, dipolar relaxation will dominate over contact. And the reason for that is if you have a high enough hyperfine coupling constant in order to enhance relaxation significantly by the contact term, that means you're usually only a couple bonds away from the metal. And if you're only a couple bonds away from the metal, your distance is really close. And it turns out that at those short distances, the dipolar mechanism still usually wins out. Okay. Now, cases where that can not be the case is when, for the dipolar relaxation mechanism, your correlation time becomes your rotational correlation time, so with a small molecule. Then with a small molecule, the dipolar relaxation becomes less effective relative to the contact relaxation, and then you might have this mechanism dominating instead. Okay? So it would not be advisable to measure line broadening in a small molecule and use that line broadening as a way to measure distances, because you're going to have a combination of contact and dipolar mechanisms for that line broadening. Okay? So that paramagnetic relaxation enhancement will really only work for a large molecule. But you can get contact relaxation in other cases. So especially if hyperfine coupling is unusually strong over a large number of bonds. All right, so if your electron spin is really effectively delocalized away from the metal, then you can get contact relaxation at those nuclei, many bonds from the metal. And at that case, then, by the 1 over r to the 6th term, you may not have as effective dipolar relaxation. And so contact can kick in. All right? So you have to be careful of that factor, too. Okay, so we have these broad peaks. So as I said, we usually want to avoid them because it means our spectra are not high resolution and they're hard to assign and they can be hard to work with. But there are a number of things that you can do either to take advantage of the line broadening, like paramagnetic relaxation enhancement, or to ameliorate the line broadening. All right, so one is, if you have really broad peaks, well, maybe you should play with them. All right, so azurin. So again, sort of worst case scenario. Very long electron spin relaxation time gives you very effective enhancement of nuclear relaxation. And that gives you these really broad lines. So I guess I don't have the assignments right here. But again, these are the histidines. Oh, I do have them. So C and D. So these are the best guesses for the assignments of these peaks are the histidines. But the cysteine you don't even see. Okay? These cysteine beta protons. All right, so in this paper, collaboration between Alejandro Vila and the Bertini lab in Florence, they were able to detect these two peaks indirectly in a really cool experiment. And I really love this paper. It has really nice explanation and discussion about electron relaxation as well. So what they did is they made a 1-to-1 mixture of copper-1 azurin and copper-2 azurin. Okay, so copper-1, of course, is D10 diamagnetic. And then we have our paramagnetic copper-2. And they just let them, you have an electron exchange between these two. So the cysteine beta protons you can easily assign and identify in the copper-1 azurin. They're at about 3.5 parts per million. And what you can do is irradiate selectively those individual nuclei. And then you let the copper-2 and copper-1 scramble. You do your electron exchange. And then that saturated peak ends up on the copper-2 instead, as when you do your electron transfer. And then, because that resonance in the copper-2 is saturated, that impacts the intensity of that peak. All right, because when you saturate it, you're going to lose some intensity because you can no longer fully excite that peak. All right, and so they're able to detect small changes in the intensity of the NMR spectrum way out in this region here. So this is from 0 to 2200 parts per million. Again, this is still a proton spectrum. So they irradiate the copper and they look at changes in the intensity of the spectrum between this region. And they saw this change in intensity peaking around 850 parts per million. All right. So this is consistent with this being our cysteine beta proton peak seen indirectly through saturation transfer. All right. So look at this monster. So it's 850 parts per million here, and a line width of 120,000 hertz. All right. So remember, usually you're collecting a 10 ppm spectrum. Okay. So this is the one that will come and eat all of your other spectra. All right. So that's very cool. So they were able to assign actually both of the protons, one at 800, one at 850, with these very long line widths, very large line widths. All right, so what do you get from that? So now we know what the shifts are, and I'll show you in a bit that analyzing those shifts can be useful. But the line width itself tells you some things. So one is that they determined that the dipolar relaxation mechanism alone cannot account for this extraordinary line width. So that tells you that the contact relaxation has to be contributing. And in fact, the contact relaxation dominates completely, which again is really unusual at such a short distance. And that is consistent with a very large hyperfine coupling constant. And that tells you that you have significant electron spin delocalization out over the cysteine, which is something that we know from other techniques as well. And we can get an even better sense of that by analyzing the chemical shifts, which we'll be doing just a little bit later. Okay. All right, so if you're not quite as brave to do those kinds of experiments, I don't know if I would have been, but you can also do things to give you lower amount of relaxation. So I mentioned before, azurine with its really broad lines, you can substitute it with nickel too, and it's still paramagnetic. But now you can directly see the cysteines without these going to these extraordinary lengths. And this then gives you a system that's easier to analyze. But of course, then you don't have the native metal, right? But you can still do a full, detailed structural analysis and do other studies on this system. So the other thing you can do is say, well, if my nuclei are relaxing really fast, I can take advantage of that. So if your nuclei are relaxing quickly, you can adjust your parameters that you use to acquire your NMR data in order to selectively enhance those fast relaxing peaks. So those of you taking the NMR practical will see a quick demonstration of that in the NMR room, where what we do is we just pulse a lot more rapidly, and what that does is it suppresses all the peaks that have long relaxation times relative to the peaks that have short relaxation times. So instead of pulsing every 3 seconds, like you might normally for NMR, you can pulse 10 times per second or even 100 times per second. And then you really just enhance these fast relaxing nuclei, and plus you can get a huge number of scans in a short period of time. So that can be really useful. So I'm showing you a 2D example, because we're doing the 1D example in the demonstrations. But this is a case where now, instead of a repetition rate, what we did is we adjusted one of the delays in the spectrum. So this is a 2D proton, nitrogen, HSQC spectrum. So we're just correlating chemical shifts of protons and nitrogens through one bond. So each peak is an amide bond, essentially, in the protein, usually, or any NH group. So this is cytochrome C again. We have the histidine that's bound to the iron, and there's an NH group on that histidine. And we wanted to determine the chemical shift at that nitrogen and hydrogen, and we didn't see it in our normal spectrum. So what we did is we decreased a particular delay, which is 1/4 times this J value here. And that then popped up that peak here. So you could do this to even more extreme values and also combine it with fast pulsing. And say if you had a large protein with really significant relaxation rates, you can then see peaks that pop up that are hidden otherwise because of the paramagnetism. All right, so you can adjust your parameters to selectively see those. So another thing you can do, if your sample will handle it, is increase the temperature. So this is usually not always feasible depending on your protein, but this will speed up any exchange, and also it will enhance your relaxation and your tumbling. All right, so this is actually a case now. I'm mostly showing you cases without exchange, but this is a case where you have an exchange process, and I'm showing the 4-heme methyls for a different cytochrome that sharpen up quite a bit when we go to actually not really high temperature, but moderate temperature. We're in 20% methanol here. And so you get a significant decrease in line widths. But this is familiar from sort of exchange processes. But you can get an enhancement, a decrease in the line widths in other samples as well. Okay. So the final thing that you can do is, rather than detecting protons, you can detect other nuclei. And again, this is something that people don't really realize and don't take advantage of nearly enough. So remember, the enhancement of dipolar relaxation is proportional to the square of the magnetogyric ratio of your nucleus. And since protons have the largest magnetogyric ratio of all the nuclei we use, they're going to be the most broadened. All right. So if you go to other nuclei, including even deuterium, even though it's spin 1, it still works pretty well for this. And it has a significantly smaller magnetic moment, carbon-13 and N15 especially, or fluorine, also fluorine-19. You detect these instead, you're going to have a much less line broadening. And in fact, the relaxation enhancement and the line widths depend upon the square of the magnetogyric ratio. So N15, you're going to have 100-fold less line broadening compared to protons. Now the disadvantage is also because of the smaller magnetogyric ratio, your sensitivity is lower. And so you have those same kind of sensitivity problems you always have with doing N15 NMR. But especially, I think this is a method that should be used a lot more, not only for proteins, but also for synthetic molecules. If you can put in an N15 or carbon-13 label into your paramagnetic compound, you may not see a proton spectrum at all, maybe, but I bet you'll see your N15s with 100-fold less line broadening. Okay? So that is something that is really something that should be considered. Okay? So again, I'm going to a little bit more exotic example, and so this is from the Bertini group where they are working with copper zinc SOD. This is a really difficult protein for being relatively large for NMR, and also having a copper 2 in it, so you have that really strong effect on line broadening. But in this experiment, what they're doing is they're detecting carbon-13, so you have 1/16 less line broadening, and they're indirectly detecting nitrogen-15. And so this then gives you peaks that really have very minimal line broadening because of this gamma squared effect. All right, so this is just pointing out again, I should have shown this earlier, the gamma squared factor in this equation. Okay, so just to summarize what I've covered with relaxation here, this tau S value is really important to be aware of. Again, the value of that is going to have a profound effect on the properties of your NMR spectrum. And so the references that I gave you have tables of those tau S values, so you can look those up. It's also helpful to be aware of for EPR, and we have sort of this inverse relationship with EPR. So if it's hard to detect an EPR spectrum of something, it's often then easy to detect an NMR spectrum, especially at moderate temperatures. So for example, low spin iron 3, you have to go to quite low temperature in EPR in order to see it because of the fast relaxation of your electron and to enhance the intensity. But the NMR spectra are really nice. But copper 2, it's really easy to get a EPR spectrum, and we all know that because you end up with those annoying copper peaks in all of your EPR spectra. But it's really hard to get an NMR spectrum of it, and that's directly related, among other things, to this tau S values. Especially it's very temperature dependent, though, of course. But although some systems are difficult, a number really show minimal line broadening, and I've summarized them here. One in particular, lanthanides, also, aside from gadolinium, really have very minimal line broadening, give you really sharp, very shifted peaks. So those, of course, we don't have those normally in our proteins, but they're really nice paramagnetic probes if you want to try to induce a shift and make use of some of these phenomena. I emphasize the using low gamma nuclei. Relaxation enhancement can give you information on distances, and we have ways to deal with this line broadening, so don't be scared. Okay, so finally, in the last bit, I'm going to talk about chemical shifts. So saving the best for last, maybe. People usually think about the really interesting ranges of chemical shifts that you get in paramagnetic systems, and these are probably the most fun to analyze. So we get chemical shifting in paramagnetic samples also through contact through bond and dipolar through space mechanisms, just like with relaxation. But the mechanisms themselves still are different. And so it's not necessarily the case that a peak that's really broad is also going to be the most shifted. So you can have a very shifted, really narrow peak, and you can have a peak that's not very shifted and that's really broad. So there isn't really any meaningful correlation between those. Chemical shifts can be to higher frequency or lower frequency. And unlike with relaxation, so I mentioned in relaxation, when we're working with metalloproteins, dipolar relaxation really dominates. And so you can usually assume that's the only mechanism. But with shifts, that's not the case. So you have to think about both these through bond and through space interactions contributing to your shifts. But it's worth it because you can get information on spin delocalization, magnetic anisotropy, and a lot of other cool stuff about the systems that those of you taking the practical are doing. Okay. All right, so these hyperfine shifted peaks that we have here, these observed chemical shifts are equal to a sum of what we would have for a shift for that same peak in a diamagnetic system that's isostructural. So now that's shielding and all of the normal stuff, plus the effect of the paramagnetic, of the paramagnetism. And this is also often called the hyperfine shift. I think in our workshop we call it hyperfine, same thing. Okay, so the paramagnetic or hyperfine shift then is primarily composed of a contact through bond. and then the through space, which is really more properly called pseudocontact rather than dipolar. And I'll be saying pseudocontact. So pseudocontact is just through space. Contact is through bond. Okay. All right, so the contact shift. So contact shift depends on things that you would probably expect now from what you've been learning here. So proportional to the hyperfine coupling constant, so that's not surprising. So this arises from delocalization of spin from the metal to the nucleus that you're observing. All right, so it's that through bond interaction that directly depends on that hyperfine coupling constant. And it depends on spin. Okay. So, and it's also inversely proportional to temperature, assuming you have a isolated spin state. Okay. So one way to find hyperfine shifted peaks sometimes is to do a temperature dependence, and you will then sometimes see peaks that have significantly greater temperature dependence of their chemical shifts compared to others. And those then are peaks that are affected by paramagnetism and possibly the contact shift. A caveat with that is this assumes a single isolated electronic state, and if you have low-line excited states like we do in the systems that are most favorable for NMR, you can have mixing of the properties of the excited state and you get curvature of this. So that's really very common to see. So it depends on spin, temperature, and it looks like it depends on magnetogyric ratio of the nucleus, but this actually cancels with a part of the hyperfine coupling constant. So the contact shift is independent of the nucleus. So contact shift for a proton will be the same as a contact shift for carbon-13. Okay, so some other things about the contact shift. So I mentioned it, you have to get spin density at the nucleus in order to observe it, and it can have a positive or negative sign, and that sign reflects directly positive or negative spin density at the nucleus. So contact shifts are most dominant for nuclei that are separated by a small number of bonds from the metal, not surprisingly. But if you're in a pi system, so for example in a heme, you can have contact shifts way out on the edge of the heme because you have these pi system that really effectively delocalize that unpaired spin out over a very wide area. Nice thing about contact shift, because it's directly proportional to hyperfine coupling constant, you can use contact shifts to estimate the hyperfine coupling constant. And some people do that. It's probably more common just to look at the pattern of contact shifts themselves and realize that that reflects the magnitude and the direction and the magnitude of the hyperfine coupling constant. Okay. So as I mentioned that the contact shift sign can be positive or negative depending upon whether you have spin up or spin down at the nucleus, and that depends a lot on the delocalization mechanism. I'm not going to get too much into this, but you have two different ways that you can get that unpaired electron spin at the nucleus. So you can have delocalization, so just directly through, so for example, if the electron is in a sigma symmetry orbital here at the metal, it can go through sigma symmetry orbitals through the ligand and then to your nucleus, and it stays spin up. But if sometimes the electron spin density is transferred through a polarization mechanism, so that's the change in the distribution of the spin up and spin down electrons in an already filled orbital, and that then can sometimes cause a alternation of spin up and spin down then as you go through different nuclei. Okay, so example of contact shift. So going back to this same spectrum, these four peaks here are the four methyls on the heme. And it turns out that the shifts of these are largely determined by the contact shift. So even though they're quite far from the iron, in terms of number of bonds, you have this pi system that moves that unpaired electron spin density effectively out to the periphery of the heme, and that gives you these large contact shifts. You also have a particular pattern of the contact shifts. So this is methyl 8, methyl 5, methyl 1, methyl 3 that I have labeled here. And that pattern then tells you the pattern of spin density delocalization. So this tells us that methyl 8, this region has the most unpaired electron spin density, followed by this pyrrole, and this pyrrole, and this pyrrole. So that tells you something about how that spin is distributed. Okay. So another contact shift example I'm showing you is this little peak here. It's really hard to see, but we have a small peak that pops up here at about 20 parts per million only in H2O in this protein, and that we assigned as a tyrosine OH So this is a group that's present in the heme pocket of cytochrome C, and we determined that the OH hydrogen bonds to the cyanide because that the shift of that tyrosine OH cannot be determined by the through space contribution to the shift, which I'll be getting to next. So the only way to account for that very large 20 ppm shift for something that's way up here is to assume that you have some through bond, some contact contribution to the shift. And the only way that can happen is if you have a hydrogen bond. So a really nice thing about the contact shift is if you determine you have a contact shift for a residue in the second sphere, you know then that you do have that second sphere interaction. And in fact, the magnitude of the contact shift can tell you something about the strength of that interaction. Yep.
Do you get a distance? Are you able to get to a distance measurement that tells you that you're in the hydrogen bond area?
So yeah, so we actually, this distance of 4 angstroms is from the proton to the iron, and that was determined by looking at the line width using a sort of the paramagnetic relaxation enhancement.
But what, your hydrogen bonds, you have kind of approximate distances for that. Are you able to? You get enough information that tells you that you probably have that hydrogen bond there?
So we do know we have a hydrogen bond because we have a contact shift. And the only way to have a contact shift is if there's some sort of bonding interaction. Yeah. But we don't know how long it is or anything like that. We just know it exists. Yeah. Okay. So another example, Azurin, I showed you the heroic efforts that were made to get these shifts here, 800 and 850 parts per million for the cysteine beta protons. And those and all of the others around here in this paper, they converted to hyperfine coupling constants. So you can determine the hyperfine coupling constants for all of these nuclei in the active site of Azurin, and that tells you about this very effective delocalization of the unpaired electron over the cysteine. This hyperfine coupling constant for the 2 protons here match very well what you get from Endor and from other methods. They also determined you have 2% unpaired electron spin density on those, which is actually, sounds like a small value. It's actually very large. And so keep in mind also that 2% electron spin density gave you 120,000 hertz line widths and 800 ppm peaks. And so if you think that you're going to take an NMR spectrum of, say, an organic radical where there is a lot of spin density at the nucleus, forget it. So we're sensitive to really small amounts of spin density. But that's part of the power of the technique is small amounts of spin density and very small changes in spin density will give you really large changes in your spectra. And so you can have sensitivity to really subtle effects. Another example in Azurin, asparagine 47 here, the backbone NH hydrogen bonds with the cysteine. So this is just another example of a second sphere interaction. And the alpha carbon here has a large contact shift. It's this peak here, and a significant hyperfine coupling constant. And that, again, is proof that you have this through bond interaction here with that second sphere interaction. Okay, and here's just one more example in, again, the copper A domain. Large contact shifts. So again, these are dominated by the contact shift over the active site. And in particular, we have very large contact shifts for the cysteine beta protons again. And so that reflects this very effective electron spin delocalization over both coppers pretty evenly. And we do know from the properties of this site that it's very much a type 3 Robin-Day site where you have complete delocalization of that electron over the 2 coppers. And that is mediated by these very covalent interactions here with these cysteine sulfurs. All right, so that's the contact shift. So I'm going to end by covering this through space pseudo-contact shift. All right, so the pseudo-contact shift is described by this equation here. All right, so it depends upon the magnetic anisotropy of the system, and then the position of your nucleus here in polar coordinates within the magnetic axes of that system. So it's not just a simple distance dependence. It depends upon distance and angle relative to the magnetic axes. And you have to have a system with some significant magnetic anisotropy. So if you have low or no magnetic anisotropy in your system, you won't have a pseudo-contact shift. Okay, so if you take an axial system, so I'm going to say our rhombic anisotropy is 0, and I'm just assuming this particular axial anisotropy, and you take a proton at 5 parts per million. So what's interesting is that proton, if you have it positioned here, 180 degrees relative to the iron here, and this is just a pseudo-contact shift isosurface here, approximately, not really calculated, but just drawn. You have 12 parts per million chemical shift here in this position. If you're here in the at this position angle of 90 degrees, you have a negative pseudo-contact shift of half magnitude. And if you're at the magic angle, you have no contact shift. So you can be really, really close to that metal, but if you're at or near that magic angle, you can have almost no pseudo-contact shift. So you have not only a distance, but an angular dependence. So that makes things a little bit complicated, but that also tells you that understanding these shifts can give you really quite rich structural information. So I'm just showing a few different examples of iso-pseudo-contact shift surfaces. So this is, again, for a completely axial system, and this is for a significantly rhombic system where x, y, and z are all different from each other. And so you get positive shifts in the dark gray and negative shifts in the light gray here. So you can, again, see both a distance and an angular dependence, and in this case, in 3 different directions. Okay, so in order to get a pseudo-contact shift, again, you need a system with significant magnetic anisotropy. And so, again, this is from this really nice review again from Ivano and Claudio. Examples of a number of different metal ions of interest, and they're magnetic anisotropies in these units. And so, for example, low spin iron 3 has fairly decent magnetic anisotropy, and as a result, you have a significant pseudo-contact shift. So this is for a proton 7 angstroms from the iron, so that's actually getting pretty far away. And this is positioned at at an angle of 0 degrees, so directly above, along the z-axis of the magnetic anisotropy tensor. Cobalt-2 is very anisotropic, so you get really large pseudo-contact shifts. I didn't show any of those examples, but if you put cobalt-2 into a zinc protein, for example, you get these really beautiful pseudo-contact shifts that you can quite easily detect, because also cobalt-2 has quite favorable relaxation properties so that you can actually see your peaks. Copper-2, different situation, low anisotropy, and as a result, very small pseudo-contact shifts. Then if you go to something like terbium, really high anisotropy and very high pseudo-contact shifts. So metals like terbium are really popular as probes. So you can, so this distance and angular dependence of the pseudo-contact shift, again, is something that people take advantage of in determining structures. So people, for example, will take a terbium compound and add it to their large protein and then measure pseudo-contact shifts and use those in order to help refine a structure. Okay. So another thing you can do with pseudo-contact shifts is if you know a bunch of pseudo-contact shifts in your protein, you can then, from those pseudo-contact shifts, determine the magnetic axes and the magnetic anisotropy of the system. And so, for example, in a heme system here, I have the z-axis coming out. Our molecular axes will have x and y line along here, but our magnetic axes may be lined like this, and we can determine that orientation and then also the anisotropies just by fitting all of the pseudo-contact shifts that we can determine simultaneously to this equation. And again, those of you taking the practical are already experts on that. So this then was developed into an iterative approach for refining solution structures. All right, so what you can do is you can first determine your chi-tensor parameters from your pseudo-contact shifts, and then feed that information into your structure that you're also calculating, and do this iteratively until your chi-tensor converges. And when your chi-tensor converges, you have a nicely refined structure. And the increase in resolution that you get in your effective resolution in NMR that you get for your structure can be really significant by doing this kind of refinement process. So this is, again, another reason that people will introduce paramagnetic probes into systems that they're determining structures on. And in fact, this is popular enough that now programs for determining solution structures of molecules automatically come with modules for doing the pseudo-contact shift refinement. Okay, so just a few things to remember as you go off for coffee and go home. Remember it longer, please. So first, I hope it's obvious now, yes, you can take spectra of paramagnetic molecules. Yes, the lines can be broad, but we are not shying away from broad lines and other methods that we use here. So why should broad lines stop us from working with NMR spectra, right? And if you're willing to delve into those line widths and those chemical shifts, you can get a wealth of information about both molecular structure and electronic structure. I spent some time talking about relaxation to emphasize this importance of this electron spin relaxation time in determining the amount of line broadening that you have. And that is something that you can have some control of, at least in terms of picking a particular system and particular spin oxidation state. And then magnetic anisotropy then determines the magnitude of the pseudo-contact shifts. Okay, so I wanted to acknowledge first all of the people who have worked with me, undergrads, grad students, and postdocs, and these are arranged chronologically, who have worked with me to develop new methods for collecting and analyzing NMR spectra of paramagnetic molecules. And these students and postdocs have taught me, I think, even more, much more than I've taught them, and I don't know if they realize that, but so maybe don't tell them. No. But Jesse's here, so he knows that. So Jesse, I have highlighted here because he's running the practical module, and so I hope that you all get to meet him and work with him. It's a really interesting interactive exercise that he developed. I also want to thank my mentors in this area. So Harry actually he was my PhD advisor, and he never actually really liked NMR, but he let me go to Florence for part of my PhD and work with Ivana, Lucia, Paolo, and Claudio. And so I did about 6 months of my PhD in Florence with their group. And I think when I came back, Harry said, maybe this NMR is pretty cool. You can get all this electronic structure stuff. So I think I might have turned him at least a little bit. And I also want to acknowledge Gerd Lamar, who was my postdoctoral advisor. And he was really the pioneer in doing this pseudo-contact shift based determination of the magnetic axes and the magnetic tensor. And he had a great wealth of knowledge as well. And so finally, with that, I want to thank all of you for your attention today, and I'm happy to take your questions.
Thanks, Cara. Are there any questions at this point?
Hi. Maybe I missed it. There was a graph you showed about how increasing the temperature and speeding up the relaxation time actually refined the peaks. Mm-hmm. And then you mentioned and alluded to how that's kind of like the chemical exchange. But typically in chemical exchange, right, as you increase the temperature, you're going to coalesce those peaks into one peak, right? And normally at lower temperatures, you'll see greater refinement. Maybe you could explain how that increasing the temperature and increasing that relaxation time, or speeding up the relaxation time, actually helps refine the peak.
Yeah, so the case that I showed you there, I couldn't find a good example of the temperature-dependent line widths. All the cases that I had some sort of weird thing about them. So I just showed that example has an exchange process. So that was actually going from sort of intermediate exchange to fast exchange. Okay. And so that was the coalescence that we saw at the top. And the broad one was the, yeah.
Okay, so if you kept going lower.
If you kept going lower, then that would get broader and eventually goes into two different forms.
Okay.
Yeah.
Okay.
Yeah.
Any other questions? There's one back there, Dean.
First of all, I'd like to say a beautiful presentation, Kara. You're a wonderful addition to this workshop. That was very clear, and I understood a lot of it. So, that was, also, another comment, I would say that you commented about Harry not believing in it or liking NMR. Ed Solomon likes it even less, and we've never turned him. Never will, I'm sure. But I did have a question about the Azurin, the beautiful Azurin story that you told about this, finding this very broad peak. Clearly, the electron exchange had to be faster than the relaxation for that to occur. That's a requirement for that to work?
Yes.
So you had to have fast electron transfer.
Yes.
Okay. And
but that worked because the electron relaxation time is so slow in that system.
Yeah, very so slow. And that slowness, is that due to the covalency? In other words, is this experiment only work because of that unique high covalency in that situation?
No, no.
Oh.
So the slowness of that, so I'm thinking about the electron relaxation is slow, actually, was what I was getting to. So you're talking about the saturation transfer experiment.
Saturation transfer, right.
Oh, okay. Yeah, so no. So you had fast nuclear relaxation, but it's not nearly as fast as the electron transfer rate.
Yeah.
Okay, so that electron transfer, that self-exchange electron transfer rate is pretty fast.
Yeah.
So, yeah.
So, but that high amount of covalency, that's not a requirement for doing a similar type of experiment in another system. Is that true?
No, yeah.
Okay.
Not a requirement at all. Yeah.
Are there any other questions? Doesn't seem to be the case. Well, let's thank Kara again.